Hello, Intro to Proofs. This is Dr. Johnson. Today is March 18th, and this is the one of two videos on section 1.2. So with this video, we're going to cover the answers to the preview activities and a few things that we rushed through our last class, which was such a long time ago. Anyway, let's go. So here is the definition from preview activity 1. However, I changed some symbols, because sometimes when I've taught this in the past, students kind of get locked in on the symbols for unknown algebra numbers, and so sometimes it's fun to mix them up. So, definition. An integer a is an even integer provided that there exists an integer smiley face such that a equals 2 times smiley face. An integer b is an odd integer, provided there exists an integer cool smiley face, such that b equals 2 times cool smiley face plus 1. And so the book uses like a n or an m there both times, and I just wanted to try something else to try to get you to think outside the box, not think outside the box, but to try to get the right impression of what these two unknown numbers are, the unknown integers. So let's use the definition above to explain why these numbers are even numbers. Well, 8. 8 is an even number because it is equal to 2 times 4. Negative 12 is an even number because it's equal to 2 times negative 6. 24 is an even number because it's equal to 2 times 12. 0 is an even number because it's equal to 0 times 2. Now, let me talk a little bit about this for a second. I'm trying to remember if someone I knew who was maybe a middle school or high school math teacher had an argument with one of their students about whether or not 0 is even. And having a strict, precise definition of even lets you know that 0 is even. There's really nothing to argue about. And that's really the beauty of mathematics, is that our definitions are clear and unambiguous. So there's really no need for argument. Okay, now explain why 7, negative 11, 51, 1, and negative 1 are odd integers. Now here, remember, our definition now, the one we're going to be using for the whole rest of the class, is that it's an odd integer if it's equal to 2 times an integer plus 1. So 7 is equal to 2 times 3 plus 1. Negative 11 is equal to 2 times negative 6 plus 1. Now look at that. Let's see, let's annotate this. Negative 11 equals 2 times negative 6 plus 1. Now notice I have to have the plus 1 there because it matches this definition. So that's why negative 11 is an odd number. Now 51 is 2 times 25 plus 1. 1 is 2 times 0 plus 1. Negative 1 is 2 times negative 1 plus 1. So I'll write that one down too, because these negative numbers are a little bit counterintuitive. Negative 1 equals 2 times negative 1 plus 1. So that's how you prove that these numbers are odd using the definition. So I might say negative 1 equals this. By definition of an odd number, negative 1 is odd. Are the definitions of even and odd integers consistent with your previous ideas about even and odd integers? Hopefully, yes. Again, that idea that I'm just imagining that middle school or high school student who was arguing about 0 being even, he might have been confused because 0 is neither positive nor negative, so maybe he thought 0 was neither even nor odd. But the definition of even is clear, so we get to say that 0 is even. All right, moving on. Oh, stop it. All right, hold on. I need to clear. Still learning, guys. Still learning. Clear all my drawings. There we go. Okay, if x and y are odd integers, then x times y is an odd integer. The proposition is a conditional statement. What is the hypothesis of this conditional statement, and what is the conclusion? The hypothesis is that x and y are odd integers. The conclusion is that x times y is an odd integer. Now, those are not statements by themselves because I never said you don't have the clearly defined let x and y be integers. But because we have, there's kind of an implied like that they're integers. So really, you could get technical here, but it's kind of pedantic. It's not worth our time. Anyway, so that's the proposition. The hypothesis is the if part. The conclusion is the then part. So if x equals 2 and y equals 3, then x times y is 6. Does this example prove the proposition is false? No, because in order to prove the proposition is false, you have to have something that satisfies the hypothesis but not the conclusion. This doesn't satisfy the hypothesis, so it doesn't mean anything. If x equals 5 and y equals 3, then x times y equals 15. Does this example prove that the proposition is true? Explain. No. The proposition is a claim for all odd integers, so one example doesn't prove anything. Part 4, what would we have to do to prove this conditional statement is true? We have to assume the hypothesis and show the conclusion must be true. To start a proof, we assume that the hypothesis is true. What will we do? Oh, that's a typo. What do we assume in this case? We assume that x and y are both odd integers. We need to prove that if the hypothesis is true, the conclusion is also true. So for this proposition, after we assume the hypothesis is true, what do we need to show? Well, we need to show that x times y is an odd integer. How do we prove that an integer is odd? Well, you have an integer, and you say, like 7, and you say, well, look, I can write 7 as 2 times 3 plus 1. So by definition of an odd integer, it's odd. That's how you prove it. Now I'm going to talk about something that's backtracking from our last class. We kind of rushed this, and I think it's important to talk about. The integers, this is called Blackboard bold, z, are closed under addition, subtraction, and multiplication. This means that if x and y are integers, then x plus y is an integer. If x and y are integers, then x minus y is an integer. If x and y are integers, then x times y is an integer. These are things you can always use from now on. They are true statements, okay? So I'm gonna finish, this is the first half of our class, and I'm gonna switch to the document camera for the second half of our class. So tune in for the second one soon.